we say that x is equal to g of t, and we say that y is equal to h of t. And basically what we want to do in this particular problem is to do the tree diagram. Okay, so if we do the tree diagram for this, at top we're going to have z. Okay, so in the middle we're going to have x and we're going to have y, and at the bottom we're going to have t. Okay, so we're going to have a branch to here, into here, here, into here. All right, so if we do with from z to x, so we're going to do the partial of z in respect to x, okay? And if we go from x to y, we're going to do the partial of y in respect, partial of z in respect to y. Now from x to t, we're going to do the derivative of x in respect to t, and on the other side we're going to do the derivative of x in respect to t. Okay, so what we're going to see is that dz dt is going to be equal to the partial of z in respect to x times dx dt plus the partial of z in respect to y times dy dt. Okay? Any questions? Okay, so next let's look at problem number 7. So in problem number 7, we want to find the partial of w in respect to u, and we want to find the partial of w in respect to v. Now, what we're told is that w is equal to g of xy, and then x is equal to h of uv, and then y is equal to k of uv. Okay, so if we start off with this one, all right, we're going to start off with w at the top. Okay, in the middle is going to be x and y, and at the bottom is going to be u. Okay, so if we draw our branches, it's going to look like so. Okay, so if we get to w to x, we're going to do the partial of w in respect to x. To get the x to u, we're going to do the partial of x in respect to u. And then we're going to do the same thing on the other side. So we're going to have the partial of w in respect to y. And then we're going to have the partial of y in respect to u. Okay. All right. So we say that the partial of w in respect to u is equal to the partial of w in respect to x times the partial of x in respect to u plus the partial of w in respect to y times the partial of y in respect to u. Okay. Now we do the other one. So we're going to start off at the top with w, x and y will be in the middle, and v at the bottom. So if we connect, so we're going to end up with the partial of w in respect to x, and we're going to have the partial of x in respect to v. On the other side, we're going to have a partial of w in respect to y, and then we're going to do the partial of y in respect to v. So the partial of w in respect to v is going to be equal to the partial of w in respect to x times the partial of x in respect to v plus partial of w in respect to y times the partial of y in respect to v. Any other questions?
I have a question. So for like number 6, how do you know that it has to be just the derivative instead of the partial derivative?
Okay, so you always have to think about it. If it's going to be a derivative, that means you're only going to have one variable. If
Mm-hmm.
it's going to be a partial, you've got more than one variable.
Oh, okay. Thank you.
Mm-hmm. Any other questions? Number 9. Okay, you're fine. All right, so let's look at number 9. Okay, so for this question, we have that z cubed is xy plus yz plus y cubed minus 2 is equal to 0. I wrote that correctly. And then we have the point 1, 1, 1. Okay. All right. And we're asked to find the partial of z in respect to x and the partial of z in respect to y. Okay. So if we start off first, if we do the partial of z in respect to x. All right. So if we do that, it's going to be the negative of, we're going to do the partial in respect to x divided by the partial in respect to y. Okay, essentially we're doing an implicit differentiation. So if we do the partial in respect to x, we should end up with negative y. Excuse me, and put parentheses here, negative out front. Don't forget that sign. So we're going to have negative y, and that's it on top. And then for the denominator, I put the wrong variable here. That's not supposed to be y. It's supposed to be z. If we do the partial in respect to z, we're going to end up with 3z squared plus y. Okay, so our derivative would be y over 3z squared plus y. Now, if we take the partial in respect to x, partial of z in respect to x and evaluate it at the point 1, 1, 1, we're going to end up with 1 over 3 plus 1 or 1/4. Oops. And did I say that was the answer? Okay. So, any questions there? And then the second part was to do the partial of y in respect, excuse me, wrong partial. Partial of z in respect to y. Well, that's going to be the negative of the partial in respect to y divided by the partial in respect to z. Okay, so the denominator of this is going to stay the same as the one above. So it's still going to be 3z squared plus y. Now the numerator is going to change since I'm doing the partial in respect to y. So I'm going to end up with negative x plus z plus 3y squared. Okay, so really we're going to end up with x minus z minus 3y squared over 3z squared plus y. And make sure I'm looking at this correctly. All right, so if we evaluate it at the if the point 111, we're going to end up with negative 3 on top and 4 at the bottom. Okay, which I said yes, and that was the answer of negative 3/4. Okay, any other questions? So next, okay, if there's no other questions, let's continue on with our material. Okay. All right. So next, what we're going to do is to move into dealing with extreme values. Okay. So, so what we're going to do is to deal with what we refer to as extreme values. And saddle points. All right. So extreme values, we've already dealt with those before. We dealt with those in Calc 1. And this is basically dealing with our max and mins. Okay. Now, saddle points are new. Okay. So to kind of help you think about what saddle points are. So basically, if I had a curve that looks like so. And let me do a little, there we go. Okay. So basically, if I had a curve that looks like so, when I'm talking about the saddle point, okay, the saddle point is going to be kind of this point here. So I kind of drew this like I was drawing the saddle, and this point here is what we refer to as the saddle point. Now, not every curve will have a saddle point, but it is a possibility that it can occur. Any questions? Now, pretty much with any extrema, okay, if we're going to find it, basically what we're going to do is we're going to set the partial with respect to x of AB equal to 0 and the partial with respect to y of AB equal to 0. Okay, so we're going to look for when these are actually equal to 0, okay, in order to determine if these are values that we're going to be able to deal with in order to determine if it's going to produce a streamer or not. Okay, so now what I want to do is we talked about in Calc 1 that there was a second derivative test. Okay, and the second derivative test was kind of it was kind of superficial as far as Calc 1 is concerned when you're dealing with only one variable. When you have a function defined in terms of just two variables. But if you're dealing with multiple variables, the second derivative test is actually crucial. Okay, so let's talk about that real quick. So, second derivative test. Okay. So, really, with this, and when we're thinking about this, we versus what we did in Calc 1. In Calc 1, we were able to run the first derivative test, determine over what intervals the function was increasing, decreasing, and determine if we basically had a critical point, which was going to be our max and min. Well, when you have multiple variables, this is a little bit harder to do. So a second derivative test is basically what we're going to use in order to help with this. Okay. So basically, with the second derivative test, we do need to look at the dealing with the second derivatives. So the first part is that if we have what we refer to as a local min, okay. So in order for a local min to occur, the second derivative the second order partial in respect to x has to be less than 0, and okay, if we do the second order partial in respect to x, times the second order partial in respect to y minus the mixed partial, second order mixed partial, if that expression is greater than 0 at the point AB. Okay, and the point AB is going to come about because of basically setting the first derivative equal to 0. So the first partial in respect to x equal to 0 and the first partial of y equal to 0, and finding those values there. So that's the point AB. Okay. The second one is dealing with and this is my fault. This is not for the min. I misread. This is for the max. Okay. It's for the max. The second one is for the local min. So for the local min, the second order partial must be greater than 0, and second order partial times in respect to x times the second order partial in respect to y minus the second order mixed partial squared. This expression must be greater than 0. And again, it's at the point A, B. Okay? So if we take a look at this, the only thing that is different between the local max and the local min is dealing with what the value of the second order partial in respect to x. If it's less than, then it's going to be the max. If it's greater than, then it would be the min. Okay. All right, next, for the saddle point, basically, if we do the second order partial in respect to x times the second order partial in respect to y minus f, the mixed order partial squared, if this is less than 0, it produces a saddle point. Okay. Now, the last thing is that if the second order partial times the second order partial in respect to x times the second order partial in respect to y minus the second order mixed partial is equal to 0, this basically tells us that the test is inconclusive. Okay, so it tells us that the test is inconclusive. Need the con inconclusive. Correct me. I'm wrong. You do need the con. Okay. All right. Any questions? Okay. So let's take a look at some examples to show you how this is going to work. Okay. So our first example, we are asked to find all local maximum minimums saddle points of the function. Okay. So for the first example, we are given that the function f of xy is equal to x squared plus 3xy plus 3y squared minus 6x plus 3y minus 6. All right, so what we're going to do first is we're going to first look at the partial of f in respect to x. So if we do the partial of f in respect to x, we're going to end up with 2x plus 3y minus 6. Okay. Now, we do need the second order partial in respect to x, so let's go ahead and do that. So the second order partial in respect to x will be what? Will be just 2. Okay. So now let's do the partial of f in respect to y. What would that be? Okay. So it would be 3x plus 6y plus 3. And then what would be the second order partial in respect to y? Just 6. All right. And then we need the mixed partial. So let's do partial in respect to x in respect to y. So what would that be? That would be 3. Okay. Okay. So here's what we're going to do. Okay. So if we take a look at this, we have that we're going to just basically go to that key portion of that equation that we're looking at uh, for the second derivative test. So second order partial in respect to x times the second order partial in respect to y minus the mixed partial squared. Okay, so the second order partial in respect to x was 2 times second order partial in respect to y was 6 minus the mixed partial second order partial was 3, and we're going to square that. Okay, well, if we look at this, it's going to be 12 minus 9, which is going to be greater than 0. So what we're going to be doing is to look and see if we're going to get a min. Okay. Any questions there? Okay, so we want to figure out where the min is going to be. Okay, now keep in mind that we do know it's going to be a min because of the fact that the second order second order partial in respect to x is 2, which is greater than 0. So this has to be positive, okay? And since this is positive, we're looking for a min. And that's just based off of the rule. Okay? Any questions? So now what we're going to do is to find where's that point at. Okay, so in order for us to do that, what we're going to do is to set the partial in respect to x and the partial in respect to y equal to 0. So we're going to have this. We're going to have that 2x plus 3y minus 6 is equal to 0. Okay, and then we're going to have that 3x plus 6y plus 3 is equal to 0. All right. So essentially, what we're going to do is to solve this system. Okay. So the first one, I'm going to rewrite it as 2x plus 3y is equal to 6. The second one, I'm going to rewrite it as 3x plus 6y is equal to negative 3. Okay. So I'm going to solve the system by elimination. So I'm going to multiply the first equation by negative 2. So if I do that, I'm going to end up with negative 4x minus 6y is equal to negative 12. Second equation I'm not touching, so I'm just going to bring it down. Okay. So if I add, I get that negative x is equal to negative 15. Divide by negative 1, so I get that x is 15. So I've got the first value. So now what I'm going to do is plug this into one of the original equations and find y. I'm going to use the top one. So I'm going to have 2 times 15 plus 3y is equal to 6. Okay. So I'm going to have 30 plus 3y is equal to 6. So 3y, excuse me, equals negative 24. So divide y equals negative 8. So there's my other one. So I only have one point, which is going to be the point 15, negative 8. And this is going to be a min. Any questions? Okay. All right, so let's look at another example. All right, so keep in mind that we only have one point. Okay, as we go through the examples, we'll get to situations that we may have multiple points, and then we'll have to check them. Okay. All right, so the next example, we have that f of xy is equal to y squared plus xy minus 2x minus 2y plus 2. Okay. No, it does not produce a saddle point. Okay. So the only way you can produce a saddle point is if that that subtraction equation is less than 0. Okay, so let's go through this and find all our partials. Okay, so if we do the first order partial in respect to x, what would that be equal to? Okay, so we're going to have y minus 2. All right, if we do the second order partial in respect to x, what will we get? We get 0. Okay, all right, so if we do the partial in respect to y, what are we going to get?
Two y plus x minus 2.
So 2y plus x minus 2. All right, so what would be the second order partial in respect to y?
2.
Okay, all right, so what would be the mixed partial?
1. Just 1.
Yes. Okay, so if we look at the formula, so again, it's second order partial time in respect to x times the second order partial in terms of y minus the second order mixed partial squared. So that's going to be 0 times 2 minus 1 squared. Well, that's going to give us negative 1, which is less than 0. So we're going to be looking at a saddle point. Any questions there? So let's figure out where the saddle point is going to happen. Okay, so to figure out where the saddle point is going to happen, we're going to set the partial in respect of f in respect to x equal to 0, and the partial in respect to y of f equal to 0. Okay, so if we do that, first one, we're going to have that y minus 2 is equal to 0. So we know that y is going to be what? It's going to be 2. Then we're going to set the partial of f in respect to y equal to 0. So we're going to have that 2y plus x minus 2 is equal to 0. But we know what y is. So we're going to have 2 times 2 plus x minus 2 is equal to 0. So we're going to end up with x plus 2 is equal to 0. So what's x? Negative 2. So the point negative 2, 2 is a saddle point. Any questions? Okay, let's look at our next example. All right, so in this example, we have that f of xy is equal to 2xy minus x squared minus 2y squared plus 3x plus 4. Okay, so first what we're going to do is say, okay, let's find the partial of f in respect to x. What will we get for that?
Uh, 2y minus 2x plus 3.
Okay, and then what's going to be the partial of f in respect to y?
2x minus 4y.
Okay, all right, so now what we're going to do is I'm going to go ahead and see if I can find the point. Okay, so we're going to set each of these equal to 0. Okay, so if I do that, I'm going to rewrite the first one a little bit. So I'm going to rewrite it as negative 2x plus 2y plus 3 is equal to 0, right? So really, it's the same thing as saying negative 2x plus 2y equals negative 3. In the second equation, I'm just going to bring down, so we're going to have 2x minus 4y is equal to 0. Okay. Now, for this one, it's actually nice in that I can go ahead and solve, okay, because I notice the coefficients on x are opposite signs. So if I solve this, I'm going to end up with negative 2y equals negative 3. So what's y? Okay, so we're going to get 3/2. So now what I'm going to do is define x, and I'm just going to use one of these two originals. I'm going to use the second equation. It's nicer. I don't have, since it's equal to 0, it's pretty nice, okay? So I'm going to plug that in, right? So if I do that, I'm going to have that 2x minus 4 times in place of y. I'm going to put in 3/2, and that's equal to 0. So 2x minus, we're going to have 6 is equal to 0. So what is x going to be equal to? 3. Okay, so the point we're going to be working with is going to be the point 3, well, let me write it correctly, 3 comma 3/2. Okay, so we're trying to see if this is going to be a, max, local min, or saddle. All right, so now before I leave this page, I'm going to go ahead and do the rest of the derivatives. Okay, so what's going to be the second order partial in respect to x? Negative 2. What's going to be the second order partial in respect to y? Negative 4. And what's going to be the mixed partial? It's going to be 2. Okay, All right, so we're going to look at those, deal with those values here real quick. So if we deal with those, again, we have this formula here. So if we plug in, we're going to have -2 times -4 minus, and we're going to have 2 squared. Yes, 2 squared. Okay, so this is going to give us 8 minus 4, which is going to be greater than 0. Okay, so if we look at this, all right, we know this is greater than 0. So since this expression is greater than 0, we're looking for either a local max or a local min. So in order to determine which one it's going to be, we go back and look at the second order partial in respect to x. So if we look at the second order partial in respect to x, it is negative. So that means this point is going to produce a what?
Maximum.
Yes, it's going to produce a max. Okay. Any questions? Yeah, so far everything has been nice, and it's been nice in the aspect of that everything is, we're only producing like 1 point. Okay, so in this next example, you're going to see what is going to happen when we have multiple points. Any questions? Okay, so let's move to our next example. All right, so we have this. We have that f of xy is equal to x to the fourth plus y to the fourth plus 4xy. Okay, so first let's start off and let's find all our partials. Okay, so what's the partial in respect to x?
4x cubed plus 4y.
Okay, so what's the partial in respect to y?
4y cubed plus 4x.
Okay, all right, what's the second order partial in respect to x?
12a squared.
What's the second order partial in respect to y?
12y squared.
And then what's the mixed order partial? That's 4.
4.
Okay, so we got everything here. Any questions here? Okay, so here's the catch that we have going on here, is that with this particular problem, what makes it a little different is that when you take a look at the second, didn't mean to do that, and decrease the size, and there we go. Okay, so when we take a look at the second order partial in respect to x, it's not equal to a constant. It's actually equal to a an equation. Well, an expression. Okay, so we can't simply just dive in and say that we know what it's going to be, because we don't know. Okay, so what we need to do is to go ahead and find all the points. All right, so let's do that. All right, so what we're going to do now is to set the partial in respect to x and partial in respect to y equal to 0. Okay, so let's start with the partial in respect to x. So, and sorry, I left off a bit. I need that there. Otherwise, this doesn't work correctly. So if I do that, I'm going to have this. I'm going to have that 4x cubed plus 4y is equal to 0. Okay. So with this, if we look at those partials, there's really nothing in common. There's no overlapping of variables that I can easily get rid of it. So what I'm going to do is to solve this using the substitution method. Okay, so I'm going to solve for y here. So I'm going to have that 4y equals negative 4x cubed. I'm going to have that y is equal to negative x cubed. Okay, and I don't want x equals because I don't want to deal with the cube root. Okay, now for the other equation, again, I'm going to have that 4y cubed plus 4x is equal to 0. But I know what y is equal to, so I'm going to have 4 times negative x cubed plus 4x is equal to 0. So essentially, I'm going to have negative 4x to the 9th plus 4x is equal to 0. Okay. So essentially, what I can do is to factor out a 4x, and I'm left with x to the 8th minus 1 is equal to 0. So essentially what I'm going to do is set each factor equal to 0 and solve. All right. So I have that negative 4x is equal to 0. So what's x? 0. Then I'm going to have x to the 8th minus 1 is equal to 0. So x to the 8th is equal to 1. So what's x going to be equal to? You're close, but not quite.
Positive or negative 1?
Yeah, it's going to be plus or minus 1. Okay, and the reason why it's going to be plus or minus 1 is because of the even exponent. Because when we do an even root, it's going to be a plus or minus answer. Okay. Now, with that in mind, keep in mind that though this is an 8, it's an 8th degree polynomial. It should have 8 solutions. It just happens that all the remaining solutions that we have are all going to be complex except for 2. And these are the only 2 that are going to be real. We don't care about the complex solutions. Okay. Any questions? Okay. All right. So what we're going to do now is to find all the points. Okay. So we have now that we have the x value. So x is equal to 0, x is equal to 1, x is equal to negative 1. And let's keep in mind that we know that y is equal to negative x cubed. Okay. So if x is 0, what's y going to be? It's going to be 0. All right. If x is 1, what's y?
Negative 1.
Mm-hmm. And when x is negative 1, what's y?
1.
Okay. All right. So the points that we're going to be checking are going to be this. So we're going to be looking at the point 0, 0. Going to be 1, negative 1. And we're going to be looking at negative 1, 1. Okay, so 0, 0, 1, negative 1, negative 1, 1. All right. So we have different points here. So what we're going to do is to plug into the formula. Okay, so we know that f of x was 12y squared. F of y was 12x squared, and then f of xy was 4. Okay, so what we're going to do is to plug in the formula. So if we plug in 0, okay, so we're going to have 0 times 0 minus 4 squared. Okay, So is this going to be greater than 0, less than 0, or equal to 0?
Less than 0.
So it's going to be less than 0. So what's going to be produced?
Maximum.
No. Yes, it's going to be a saddle point. Okay. All right, next we're going to plug in and we're going to deal with the point 1, negative 1. Okay. So second order partial with respect to x is going to be equal to 12 times. The next one is going to be 12 minus 4 squared. Is this going to be greater than or less than 0?
Greater than 0.
Okay, so it's going to be greater than 0. So since it's greater than 0, we're going to be looking for if it's going to be a max or min. Okay, well, that's going to be dictated based on what the value of the second order partial in respect to x. Well, the value of the second order partial in respect to x at that point is 12. So that's greater than 0. So this is going to produce a what?
Minimum.
It's going to produce what?
Minimum, right?
Yes, it's going to be a min. Okay. So now we're going to look at the last one. We're going to plug in, deal with the point negative 1, 1. So if I put negative 1, if I evaluate the second order partial in respect to x and with the at 1 at the point, I'm going to get 12. This second order partial in respect to y, I'm going to get 12 minus 4 squared. This expression is the same expression as above, so it's going to be greater than 0. So again, I look at the value of the second order partial in respect to x. It's 12, so it's greater than 0. Since this is greater than 0, we know it's going to produce a max or min. This is positive, so it produces a min. So basically here, we've got that 0, 0 is a saddle point. 1, negative 1 is a min. Negative 1, 1 is a min. Any questions? Great. Okay. All right, so the last thing we're going to take a look at, the last two examples we're going to take a look at is dealing with absolute maximums and minimums, okay? But before we move into that, at this time, let's take a 10-minute break, and then we'll come back, we'll start on that. Okay, so let's look at our next set of examples. So in these examples, we're going to find the absolute max and mins of the function on a given domain. Okay, so just keep in mind, there's no such thing as an absolute saddle point. So saddle point is only going to happen if we're just dealing with local max and mins. When we get ready to do absolute, it's just the max and mins that we can focus on. Okay, and we normally try to put it on a region so we can deal with it. All right, so let's take a look at the first problem we have. It tells us that d of xy is defined as x squared minus xy plus y squared plus 1, okay? And it's on a triangular triangle plot in the first quadrant, bounded by the lines x is equal to 0, y is equal to 4, and y is equal to x. Okay, so the first thing we're going to do is we're going to graph our region that we're going to be focusing on. Okay, so dealing with x is equal to 0, this is going to focus on being the y-axis. Y equals 4. We're going to go up 4 units, so 1, 2, 3, 4. And we're going to have a line here. And then y equals x. We're going to have the point 0, 0, 1, 1, 2, 2, 3, 3, and 4, 4. Okay, so it's going to be, this. Okay, so this is going to be our region. All right, and what I'm going to do with this region is to label the endpoints. Okay, so if I do that, this is the origin, so we're just going to label it O. Okay. Next, we're going to label this point here as A and this point here as B. Okay. All right. So what we're going to do is we're going to basically move around this region along its sides. Okay. And to take a look at what's happening. All right. So the first way we're going to go, we're going to take a look at going along the region from O to A. So we're going to look at the segment, not OA, OB. Okay, we're going to look at the segment OB. Okay, so if we're looking at the segment OB, all right, keep in mind this is made up of the line y is equal to x. Okay, so that means that I can now rewrite the function instead of in terms of xy, it will be in terms of xx. And here's why. So along the line, it says that y is equal to x. So in place of y, I'm putting x in there. So now what I'm going to do is to rewrite the equation. So I'm going to end up with x squared minus x squared plus x squared plus 1. So really, d of xx is equal to x squared plus 1. Okay, so now in order to deal with this, because we're trying to do max and mins, I need to find the first derivative. So if I find the first derivative, I'm going to end up with 2x. All right, and keep in mind that in order to find a max and min, I set the first derivative equal to 0 and solve. Okay, so I've got 2x is equal to 0. So x is 0. Okay, so along the segment 0, 0, when x is 0, oops, sorry. When x is 0, y is going to be 0. That's going to be at the origin. So one point that I'm going to have is the point 0, 0. Okay. Now, the point that we are given is an endpoint. It doesn't give us anything in the middle. So what I got to do is also work with the other endpoint. Well, the other endpoint is here, and which is going to be 4, 4. All right. So what I'm going to do is I'm going to evaluate my new function at the endpoints. So if I find d of 0, 0, I get a value of 1. If I evaluate the function of d at 4, 4, I'm going to get a value of 17. Okay. Any questions there? Okay. So next, I'm going to work my way around the triangle. So my next region I'm going to deal with is the segment AB. Okay. So if I deal with the segment AB, right, for the segment AB, there's something that's set. What is set? So along the segment AB, something is set. What is set? Yeah, y is 4. So y is set as 4. So what I'm going to do is to rewrite this equation where I make the y value set at 4. So I'm going to have that d of x4. All right. So now what I'm going to do is to write this equation. So it's going to be equal to, we're going to have x squared minus 4x plus 16 plus 1. Okay. So now, again, I need the derivative of this. So if I take the derivative of this, what will I end up with?
2x minus 4.
So I'm going to get 2x minus 4. And now, again, in order to find the max or min, we set the derivative equal to 0 and solve. Okay, so I'm going to have that 2x minus 4 is equal to 0. So what's x? 2. Okay, so what I'm going to do now is to check all the values. Now, when x is equal to 2, if I look at this, is it one of the endpoints? No, it's something in the middle. Okay, so it's going to generate a new point. So what I'm going to do is I'm going to look at d of 2, 4. But I'm also going to check the endpoints. So one of the endpoints is going to be 0, 4. And the other endpoint is going to be 4, 4. Okay. Now, I'm going to look at this, and let me rewrite this in a simplified way. So x squared minus 4x plus 17. Okay. So if x is 2, so if I plug 2 into here, what value will I get? I'm going to get 13. Okay. So next, if I plug 0 into here, what will I get? I'm going to get 17. Okay. Now, I already know what d of 4, 4 is, which is what? 17. Okay, so I've got all the values that are created along the segment AB. Okay, any questions? Okay, so if I go back and look at the triangle, what's the last segment that I'm missing here? Oh, AO or OA. Okay, I'm missing that segment. So now I'm going to go along that segment. So if I go along that segment, all right, let's think about this. So going along this segment AO, what's set? So going along the segment AO, what's set?
A is equal to 0.
Say again?
A is equal to 0.
Yeah, x is 0. So what I'm going to do now is to rewrite my function with that set value. So I'm going to look at d of 0, y. Okay, look at d of 0, y. So if I look at d of 0, y, I'm going to have 0 squared minus 0y plus y squared plus 1, or just y squared plus 1. So if I take a look at the derivative of this, what will I end up with?
Do we have to take a derivative of x or y?
We're taking derivative with respect to y.
Oh, it's going to be 2y.
It's going to be 2y. Okay. And again, we'll set this equal to 0. So if we set this equal to 0, we have that y is what?
0.
Y is going to be 0. So now 0, 0 is one of the endpoints. Okay. So if I look at d of 0, 0, what value am I going to get? I'm going to get 1. Now, the other endpoint would be d of 0, 4. Okay. Now, if I do d of 0, 4, we've already done that, and that's going to give us a value of what? 17. Okay. So now I'm ready to answer this. Okay. And what I'm going to focus on is going to be all these values here that I got. Okay. So that's going to be my main focus. Okay. So if I look at all the values, what is the maximum value that I'm getting? It's 17. Okay. So what I would say is that my absolute max of 17, it happens at, so what points does that maximum value of 17 happen?
Zero, 4, and 4, 4.
Right. So 0, 4, and 4, 4. Okay. Now, for the absolute min, it's going to be the smallest one. So the absolute min of what? What's the smallest value that I get for the function?
1.
1. And that happens when?
0, 0.
At 0, 0. Okay. So this is what I get for the absolute max and the absolute min. Okay. Any questions there? Okay,
So,
so
so
go ahead.
when we're doing the point AB, like why do we find the point 24, like the line AB? Because yeah, like why do we find the point 24?
Well, x is already set. I mean, y is already set at 4. And we found that from the first derivative, we've got an x value, and set the first derivative equals 0, we found the x value equal to 2.
Okay, I see. All right, thank you.
Okay. Uh-huh. So let's remember, when you're doing absolute max and mins, okay, you do have to find any critical, you need to find any critical values that are going to occur, okay, and you also need to check the endpoints, okay. So in this case, for the segment AB, we ended up having a critical value that occurred that wasn't the endpoint, so that's why we had to check it. All right, does that make sense to everyone? The critical values are basically the values you get when you set the first derivative equal to 0 and solve for the variable. Okay. All right, so now let's take a look at another example. Okay. All right, so in our next example, all right, same thing. We are going to find the absolute max and min values and where they're going to occur at for the function on in this case, it's going to be a rectangular region. Okay, so in this example, we're told that f of x, y, is equal to 4x, y minus 32, x cubed minus 24, y squared. Okay, so, and we're given that the rectangular region is defined at x is between 0 and 1, and y is between 0 and 1.
I think it's 48xy.
Oh, it is. Okay. There we go. Okay. So now, what I'm going to do is to draw the region so I can see what I'm dealing with here. Okay. So x is bounded between 0 and 1. So here's 0, here's 1. Y is bounded between 0 and 1. Again, here's 0, here's 1. So basically, what I'm going to be dealing with is going to be dealing with this square. Okay. And for the square, I can label the vertices of this. So I'm going to call this O. Say this is A, this is B, this is C. Okay. And basically what we're going to do is just go around here. Okay. So I'm going to start off with the segment OA. I'm going to start off with the segment OA. All right. So if I start with the segment OA, what is set? What coordinate is set?
is equal to 0.
Yeah, x is set and it's going to be 0. X is set and it's going to be 0. So what I'm going to do is I'm going to look and create the function where it's 0 comma y. Okay, so if I create the function 0 comma y, I'm just going to have negative 24y squared. So essentially what I'm going to do is find the first derivative of this. So if I do the first derivative, what am I going to get?
Negative 48y.
And again, set the first derivative equal to 0 and solve. So I'm going to get that y is equal to what?
0.
0. Okay. So now what I'm going to do is to evaluate the original function at 0, 0. Okay. Well, I realize that 0, 0 is one of the endpoints. So I do need to also evaluate the other endpoint. The other endpoint is going to be f of what? 0 what?
1.
F of 0, 1. Okay. Now, I'm going to look at this simplified version. So at 0, 0, what value do I get? I get 0. At 0, 1, what value do I get? Negative 24. Okay. All right. So this is what I get off the first segment. All right. So the next segment I can deal with is what?
AB.
Okay. So I can deal with the segment AB. All right. So if I deal with the segment AB, I'm going to start it right here. Okay. Now for the segment AB, what is set?
Minus 1.
Y is 1. So I'm going to look at f of x comma 1. All right. So if I do that, I'm going to end up with 48x minus 32x cubed minus 24. Now, if I take the derivative of this, what will I end up with?
48 minus 94x squared.
Be 96x squared.
Yeah, 96, my bad.
Okay. And then what I'm going to do is to set this equal to 0. Okay. So let me move to the next page. All right. So I'm going to have that 48 minus 96x squared is equal to 0. So I'm going to have that 96x squared is equal to 48. X squared is equal to 1/2. So what's x going to be?
1 over square root 2.
Yes, but a little bit more.
Plus or minus.
Plus or minus. So plus or minus 1 over the square root of 2. Now, let's pay close attention, okay? So we know that x is bounded between 0 and 1, okay? Do both of these solutions work? No. So which one do I get rid of? I get rid of the negative because it's not within the boundaries that are already set for us. Okay, so it's just going to be x is equal to 1 over square root of 2. Okay, so with this, that's a value that I have to check. So I'm going to look for f of 1 over the square root of 2. Now, we already said that y is set at 1. Now, that's not one of the endpoints, so we need to look at everything else, okay, the other pieces. So one n is going to be, we're going to look at f of 0, 1. And then we need to look at the other end, which is going to be f of 1, 1. Now, for this function, it was defined as 48x minus 32x cubed minus 24. Okay, so let's deal with the easy ones first. So if x is 0, what value will I get?
Negative 24.
Okay. If x is 1, what value will I get?
Negative 8.
Is that right? Yeah. Okay. All right. So now let's take a look at it when we do f of 1 over the square root of 2. So if we plug that in, we're going to have 48 times 1 over the square root of 2 minus, we're going to have 32 times 1 over the square root of 2. We're going to cube that. This is a 2. Okay. And then minus 24. Right? So just use your trusty calculator, and what value do you get? And go to 2 decimal places, please. You got negative 1.7, 1.3, 7. Okay. Everyone agree with that? Okay. All right. So we've taken care of 2 sides. All right. So what's the next side we can deal with?
BC.
Okay. So if we deal with the side BC, okay. So for the side BC, what is set?
X is 1.
Okay, x is 1. So we're going to look at f of 1 comma y. Okay, so we're going to look at f of 1 comma y. So if we look at the f of 1 comma y, what is the function going to be?
A 48y minus 32 minus 24y squared.
Okay, so this is going to be our function. So we need to find f prime of 1y. So f prime of 1y is going to be what?
48 minus 48y.
All right, and we're going to set this equal to 0. So if we set this equal to 0, what's y?
1.
1. Okay. So we're going to be looking at f of 1, 1. All right. Now, is 1, 1 an endpoint on that segment? So is 1, 1 an endpoint on the segment BC? Yes, it is. Okay. So we have that, but now we need to check the other side. So if we check the other, what do we have?
0, 1.
Okay, so 1, 0. Okay.
Oh, yeah, 0.
All right. Now we already know what the function is evaluated at 1, 1. Okay. So what was the value of the function at 1, 1? Negative 8. All right. So now if we look at 1, 0, what would be the value?
Negative 32.
Negative 32. Any questions? Okay, so now we've got one more segment to look at, and that is the segment of OC. Okay, now for the segment OC, back, what's set?
Y is 0.
So y is 0. Okay, so we're going to look at f of x comma 0. All right, so with y being 0, what's my equation? With y being, yes, with y being 0, go ahead.
Negative 32 x cubed.
Right, so negative 32 x cubed is going to be my equation. So now we need f prime of x comma 0, which is going to be what?
Negative 96 a squared.
Right? And if we set that equal to 0, what's x?
0.
Okay, so our point that we're going to be looking at is 0, 0. Well, we've already dealt with 0, 0. Okay. So at 0, 0, we know the value is 0. And the other extreme, which is the other endpoint in this case, is going to be 0,
1 0.
1, 0, which we know that's going to give us a value of negative 32. Okay. Any questions? Okay. All right. So with this one, we have to be a little cautious because we're not. We may be missing something here. Okay. As far as the max is concerned. Okay. So in this particular problem, we are going to go and check and see what the critical points are. Okay. If there's any critical points based off of doing the partials. All right. So what I want to do now is I want to find the partial of f in respect to x. So if I take the partial of f in respect to x, what will I get?
48y minus 96 a squared.
Okay. And then I want to look for the partial of y in respect to, partial of f in respect to y. What would that be?
48x minus 48y.
Okay. And keep in mind, in order to find the point, we set h equal to 0. Okay. So if I deal with the second one, I'm basically going to get that y is equal to x. Okay. So I'm going to use that in order to deal with this first equation. Okay. So with the first equation, I'm going to now have that 48x minus 96x squared is equal to 0. So I'm going to have that 96x squared. Oops, hold on. Bad solving. All right. So for this, what I can do is factor out a 48x. So I'm left with 1 minus 2x is equal to 0. So set each factor to 0 and solve. So I have that 48x is equal to 0. So x is equal to 0. We already have that accounted for. The other one is we're going to have 1 minus 2x is equal to 0. So x is equal to 1/2. Okay. Well, if x is 1/2, y is going to be what? So if x is 1/2, y is going to be what? 1/2 also. Okay. So we have a new point here that is not on, that's not going around the edges. And this point falls within our defined intervals here. Okay. That point falls within our defined intervals. So it's something that we need to check. So if I look at f of 1/2, 1/2, if I look at f of 1/2, 1/2, if you evaluate the function at this point, what will I get? Yeah, we get a value of 2. Okay. So now let's look. Okay. So for the absolute max, what value do we have? So what's the absolute maximum value? It's 2. And it occurs at what point? One half, 1/2. Good. All right. And then absolute min, what's the value for the absolute min? It's -32. And it occurs at what point? At the point 1, 0. Any questions? Now, I'm sure you may be questioning, why didn't we do this on the last one? And let's look at the last problem and let's look at it real quick. And if I look at the partials. So if I look at the partial with respect to x, I'm going to get 2x minus y. And then if I look at the partial with respect to y, I'm going to get negative x plus 2y. Okay? So if I solve this system, okay, so I'm going to have 2x minus 2y, excuse me, bad writing. 2x minus y is equal to 0. The second one, if I'm going to go ahead and multiply by -2, saying negative 2x plus 2y is equal to 0. Well, this is going to give us 0 equals 0. So it tells us absolutely nothing. So this is why we didn't really worry about this, because this is what's going to happen. Okay. So always my thing is that do check and make sure you don't have any points produced from the so you check and make sure you don't have any other points produced, because if you do need to also take in consideration of those, because they are critical values that you need to check. But if it does happen to produce something, you do need to make sure that it is within the region that you have defined, because if it's not, you don't have to check it. Okay. Any questions? Okay. All right. So that is it for today. Okay. So you need to, oops, back to the beginning. Right. So you need to work on extreme value and saddle point homework. Okay. Also, quiz 9 is going to be available and it's due Tuesday. Okay. Midterm is on Thursday. Okay. So on Thursday, there will be no class. All right. You will just be doing your midterm and everything. Okay. Any questions? All right, guys, you have a great rest of your day. Have a great weekend, and I will see you on Tuesday. You're welcome.